Hi, so thanks everyone. I'm very happy to be here to present a kind of a very practical case study of a project we did recently for the Canadian government actually, where we're trying to take a large amount of free text data and kind of run a whole data pipeline and NLP and AI case study to extract insights. So it's quite actually a typical project in some sense, but it's interesting because it's a kind of very clean workflow that shows kind of how powerful and how productive you can be with Python to achieve really practical results in a very short amount of time. So just about myself, I'm currently working at a company called Aiden.ai, which is based in London, and we make a virtual colleague for marketing. And actually this project I did outside of this, it was a kind of something in my free time. My interests are kind of in NLP and speech recognition and machine learning, and I like working with Python because the library and tooling and tools you have available really speed you up and save you a lot of time. So at this talk, basically, we're going to go through 4 stages. Firstly, we're going to look at what is the problem we're solving and what solution did we propose. How did we handle and pre-process the data? Then, which machine learning models and analyses did we do? And finally, what results were we able to achieve? So firstly, have you ever seen these kind of surveys where when you go to a shop or you get a link, someone's asking you, how was your experience? And the problem with these surveys that you get is sometimes they can go for a while, and they can get longer, and sometimes they can get a bit too long. So this is a survey from BestBuy.com, an electronics store in the US. When you buy something, they say, do you want to answer a few questions? And here they're asking you, I think, 30 questions in a few paragraphs about your experience. And you can imagine the problems here. I mean, if you're answering 30 questions, at some point you're going to get bored, you're going to start lying. I'm actually surprised that many people even finish this survey. And your data quality is going to be more noise than insights, so it's going to be pretty much useless. And when you read the responses people give, they say stuff like this: I don't know, it's just garbage, it can't be, there's just nonsensical data there. And it's basically, if you're an analyst and your job is to look at thousands of responses like this, it's going to be exhausting and it's very hard to actually get any kind of real information out. And actually, from the provider side, so the people running the survey, we talked to some of them and they said that the data is so wild and it's so hard to interpret manually that they sometimes just walk away from the data. So they have all this information from the customers about the service and how to improve what they like, what they don't like. And sometimes it's so painful to analyze it, they just leave it completely. So this is really a shame. It's a big waste. So, we thought about what is a better way than asking them 30 questions and fill out a huge survey with very bad information. And we said, what if instead we could do a survey just like this? 2 questions. What do you think and how did you feel? So, just a simple free text response and then a rating out of 5. And it seems kind of obvious, so why doesn't every company just do this already? The problem is, as a customer, we'd all rather do the second one. You can kind of just leave it blank, or you can just speed through in 5 minutes, or you can spend 30 minutes. It's as detailed as you want. But from the side of a company, if you give just a free text box, basically you're forcing them to put an analyst on to read every single response and then think about it and produce a report in the end. Because at least when you have this massive survey, you can just take everything, put it in Excel, make some charts, and the charts will have nonsense data, but at least there is a chart, so your boss will be happy and you won't get fired. But if you do have a free text response, you have to actually sit through and analyze and structure and code everything, which is expensive, it's hard. So people just want to avoid that, and that's why they don't do something kind of intelligent when it comes to surveying. So, like I said, it's difficult because you have to be uniform. It's expensive because you have to spend a lot of time going through every response, and it's basically impossible at scale. And you actually have a lot of bias because when you have an analyst looking at every response, the person has an idea in their head of what they want to see and what they want to report to the boss already. So they're gonna selectively filter how they report things. So, in any kind of case where we have this process, which is very labor-intensive and fragile and difficult with humans, but also very boring and mundane and repetitive, machine learning is a very good tool, and Python has a very good skill set, tool chain to make this extremely simple for us. So, first we can say, okay, let's do some topic modeling. This is breaking up our text, our documents into automatically into clustering them into topics. But the problem is normal topic modeling is unsupervised. You can't, it's not interpretable or actionable. So we said, okay, let's combine that with some automatic summarization techniques, which reduce a large body of text into a small body of text. But then still, we don't really know how important are these relative to each other. And then we said, let's throw in some classical statistical analysis, and then hopefully we have a good workflow. So, on the high level, we're looking at something like this. And it's quite simple, but in the end of the day, what goes in at the top is the survey responses, those little free text documents each person said. And at the very bottom, we say, what is each topic? What is a small summary of what people said in this topic? How satisfied are them out of 5? And how frequent do people talk about this topic? So that's what we want to get to, some very simple top-level summary. And there's a workflow we're going to go through that's basically the content of this talk. So actually, pre-processing, it's kind of the most boring part of data, but everyone knows real data scientists spend 90% of the time on pre-processing. And actually, what really surprised us was when we were tuning our models, pre-processing was a single thing that affected our accuracy the most, more than any kind of hyperparameter, more than changing our models, more than making anything deeper. It was just cleaning the data better was always the largest impact for us. So that's kind of why I thought it was very good to have an actual dedicated section talk about it. And it's very basic. This is basically a workflow you use for any kind of free text data. The first thing you do is, computers can't understand English words. It's kind of meaningless for them. So we have to represent them into some kind of vectorized and numerical format. So we use, the most common is bag of words, which you may already know, which is you just take the sentence, you destroy all the order, and you just put it in a vector. And actually, it's just every index in a vector is a word, and the value is just how many times it appeared. So it's like a 1, 0, 1, 0. It's a binary array. And that's it. You just count it and just throw it in a vector. This is not great, it's not perfect. So if you get the word toy dog and the word dog toy, they have completely different meanings, but they vectorize them exactly the same way. So you lose all all ordering. But this is some kind of dimensionality reduction. And even though this is a weakness, we can kind of live with it. If you want to avoid it, if you have some kind of use case where it's very important, you can use deeper models like word embeddings. But actually, a lot of cases, this is fine. Another one is that actually sometimes you have two sentences that mean basically the same thing. So buying old cars and purchasing used automobiles, it's very similar meaning, but the vectorization is completely different. And again, there's other techniques like word embeddings, but in a majority of cases, this is actually good enough and it's very easy. And the other thing about cleaning natural language data you have to be very careful about is normalization. So in most languages from the Western world, we have a lot of morphology. So we change words, conjugate words, pluralize, make them masculine or feminine. But in the end of the day, from a semantic or meaning point of view, it doesn't matter. Like all these words are basically the same. And so we want to change them all into a canonical form. So actually, note is that if you are working with massive data sets, like if you're working with Google's gigaword data set or all of Wikipedia, there's so many occurrences of every kind of word that it doesn't matter, you don't really need this. But in most cases, like we're working with a couple thousand samples, if you don't do this, your data is going to be too sparse, your vocabulary will be too large, and you won't have enough training data. So this really increases the efficiency of small data sets. And there's kind of two techniques. One is called stemming, which is rule-based, and this actually makes a lot of mistakes, but it's very, very fast and simple, where you just look at what are the rules in the English language, and you just chop parts off because you think it follows a grammar rule. And it's kind of guessing. And the second one is called lemmatization, which is dictionary-based, where you actually look up the meanings of words. So, example here, the word provision got lemmatized into the word to provide, which is not obvious unless you have a dictionary with you. So this is a very important step to reduce the dimensionality of your data. And so in practice, what we do? We just kind of, like I said, Python has great tools. So for lemmatization, we just we load something called the WordNet lematizer. So WordNet is this very great corpus made by Stanford, where they basically created all the words in English language and also in other languages, and they link all the meanings together. So it's a very, very strong NLP corpus for many use cases, including lemmatization. And you put in, for example, we say lematize the word appeared, and it comes out as appear. So it's very simple. You just have a simple API, and you can just, it's already part of NLTK, which is a very famous natural language processing library. Then what we do is we just need to turn it into that vector of words, that bag of words. So what we do is from NLTK, we just import the, is it a pointer? Yeah, we import the count vectorizer, and we just put all the words, we put the tokenizer in. The tokenizer just splits it up by white space and punctuation, and then we just say fit transform, and that's it. So we have 3,000 samples at 2,000 vocabulary size. If you want to see what words are, you just say get feature names. And you can see here, so if you vectorize and your first index is a 1, it means you have a word ability appeared one time in your sentence. And you can see there'll be about 2,000 words here. And actually, during the data cleaning, we threw out about half our data because it was too small, too long, irrelevant, or messy, or garbage. So the cleaning was the most important step for us. And another thing that is actually a problem for most of the world is that most countries are multilingual. So you'll get responses in different languages, and you have to run the whole workflow multiple times in each language. So in our case, we had English and French. So it's very simple. We need to know if some proportion of the words in the sentence are in the dictionary for English or French, more than like 50%, 80%, then we keep them, otherwise throw it away. And Python actually has a great library called Lang detect. You just import it, and it will just tell you, is this English, is this French, is it Russian? And it just goes. So that's it. That was the cleaning of the data. And now the actual fun part, which is the analyses. And a really important aspect of analysis is that in Python, because everything is already there, it's easy to fall into this trap where we just say, oh, here's an API, I'm just going to call it, without actually knowing how the API works underneath or how the algorithm works. So it's going to be a bit of information about that. So one of the main ones of topic modeling is LDA, which is latent dirichlet allocation, which is, Wikipedia says it's a generative statistical model that allows a set of observations to be explained by unobserved groups that are similar, that explain why some of the data is similar, which looks, it's very obtuse and kind of complex, but actually it's a very simple definition. So we're saying it's a generative model, which is different from a discriminative model, which means we're learning the distribution between our label and our data, but in both directions. We can go forward and backwards. We can go from data to label and labels back to data if we want, whereas discriminative models only go from data to labels. It's also using observations. This just means we need some kind of training corpus, so we need some examples, but it's unobserved, which means it's unsupervised. So no one has to go through and label any of the data ahead of time. And finally, the objective of the algorithm is to find similar results. So this is basically the goal of the algorithm is to find clustering by similarity. So it's a quick example is if we took the movie transcripts of these 4 movies, the Hangover, Star Wars, Star Trek, and Avengers, LDA might come out with some kind of matrix like the thing on the right, where it says, okay, this Hangover has topic 0, 90%, not very much for the others. Star Wars and Star Trek are very good on topic 1, and Avengers is very good on topic 2. But actually, you notice, it doesn't tell us what 0, 1, and 2 are. It just says, this is how I think I would cluster them. And so the human goes in and says, well, I think this is a comedy topic, I think this is science fiction, and I think this is action. But you notice this is just kind of a human just ballparking, guessing, and putting their own interpretation, which is fragile, doesn't work at scale. So it's getting us, it's good because it's putting some kind of structure onto our data, but it's not all the way there yet. So at the high level, you just kind of input a bunch of documents, and you train it over time, and at the end, you get those kind of topic grouping segments. And to kind of understand how it works, it's actually a very simple algorithm. So imagine we have Elon Musk is very successful, and we make our mission to Mars, and we get there and we discover the Martians are dead, but they have a library, and we find all the books, and we find they have an alphabet, and we want to know what genres do they have. So we have 3 things: we have words, we have books, and we have genres. So already we know how words relate to books. We have a distribution because you open a book up, you count how many which words are in it, and we already have a distribution of words from books. But we don't know how books map to genres. So what we say is basically we just guess first. We go through every single word in every book and say, I think this is genre 1, this is genre 2, this is genre 3, and we just guess randomly. And already, by guessing this, by guessing the link between words and genres, we implicitly have a link from books to genres as well, because you just say, for this book, what do most of the words, which genre do they fit into? But it's a guess, and it's actually, for a big book, it'll be approximately equal at the beginning. But then what we do is, since we've rolled the dice for every word, we keep shaking the dice. But this time, instead of shaking a fair dice, we shake a weighted dice. And the weight has two components. One is for every time the same word appears somewhere else for a topic. So for the word hospital, every time it appears with topic 0, the next time I roll the dice for word hospital, it has a slightly higher chance to appear with topic 0. And the second one is we weight it by the whole book. So we're saying every time the word topic 0 has appeared in this book, and this word is also in this book, I'm going to give it a higher chance. So basically, you have two weights. One weight is inside a book. All books inside the book tend to gravitate towards the same topic. And second is a global weight, which is all words tend to gravitate towards the same topic. So this means globally, topics become uniform. The word hospital will become the same topic in every book. And secondly, typically we mention the same words inside topics. So the word hospital and doctor will start gravitating towards the same book because they're co-referenced a lot. So that's it. Basically, you roll weighted dice with these two influences, and you just keep shaking and shaking for lots of generations, and eventually they start gravitating towards topics. And that's the whole algorithm, actually. So it's very simple, and in practice, sklearn and a few other libraries have great LDA models. We just construct our model with a few hyperparameters like concurrency, verboseness, how many iterations you want to train for, and we just run fit, and that's it. But that's kind of a risk. It's so easy that sometimes it's hard to know how it works underneath. And you run the fit, and it just goes through iterations, and you can see the score going down, which is the error. So it gets better over time, and then once the error is low enough, it just stops training. And actually, like we said before, it's a joint distribution, so we can go from labels to data, and data's back to label. So you can see here, not only does it give us the topics per response, but also we can get for each topic what words were used a lot. So that's it. If you want to classify a book, you just call .transform on it, and it will give you the topics. So actually, the first time we ran this, you look at this. This is the responses we got from the first topic. It said something about recycling, something about birth certificates, something about transport, and something about national parks. So it's a bit strange, and we thought, okay, this is not really working. How can we improve? And the reason it's really bad is because for every response, actually, the topic scores always sum to 1. So even if something is garbage, like this response, whatever the survey was lame, the scores for the topic still have to sum up to 100, just as much as we need more highly trained staff in hospitals. So you can see here, just LDA by itself is a bit nonsensical, because even noisy things have the same score as useful things. So we need to make an improvement. So one thing you can do is rank relevance, where you say, I'm going to multiply the score of that topic by also how often the main words of that topic appear in the sentence. So basically, because we have a word hospital, this one's going to boost the score of LDA, of healthcare, and staff, it's going to boost the score of a staff topic. But because this has no words that are actually highly important to any of these topics, the relevance score goes down a lot. So here, now we can see there's a huge difference in relevance scores between these two, because the most important words in this topic have appeared in the sentence. So it's a very important cleaning step to kind of add some relevancy to LDA. And then finally, we just sort it by how relevant they are and just chop off another section. So as you can see, what we've done is we've actually chopped off data twice. So we're throwing away data many times, but actually the intuition is that having less data of high quality is much better than having a large amount of noisy data. Because, I mean, this talk was all about large, noisy corpuses. And finally, LDA just gave us those ambiguous topics, so we need to put some actionability and insight on top. So we want to summarize the documents, and summarization should be short, it should capture the most essential ideas of a corpus, and it should be in natural language. And a really kind of great technique you can use is something called LexRank, which actually is very simple too, but I guess, so here's an article from a BBC where it's just kind of something about, I don't know, David Cameron, the Treasury, something about finance, and the LexRank will take this whole report and say, the BBC understands that the Chancellor, along with the Treasury, will retain the responsibility. So it turns a big thing into a small, essential sentence. And the way it does this is actually very easy to understand. Every sentence is a node in a graph by bag of words, and you encode it with bag of words just like we did before, and then we draw links between every sentence to make a densely connected graph. And the strength of a link is basically how many words are shared in common between two sentences. And then we do the PageRank algorithm. So PageRank is, a famous Google algorithm where we say the strength of any node is equal to the sum of the strength of the links times the strength of the other nodes. So this one gets bigger if it's connected strongly to other big nodes. So that's it. We just run the PageRank. It's a recursive scoring algorithm, and then we'll eventually have what are the top scoring sentences in our corpus. So in practice, there's another great library called Summy, and it has a bunch of summarization algorithms, including LexRank. And you can import it, and they all have the same API, so you can kind of run through all of them to see which one works for you. All we have to do is we do the same thing. We have to run out stemming again, just like the previous one. We do the same bag of words, and then you just call summarize on it, basically. And then you have your short sentences. So finally, let's look at the results. So here we go. This is how many responses in our survey came to each topic. So you can see people mostly talked about topic 6, topic 1, topic 13, and topic 14. If we dive into the topic, you can see what are the top words in each topic. So in topic 4, people were talking about doctor, care, government, health, hospital. And you can see already we have some kind of intuition that people are talking about healthcare, but we're not actually sure what are they saying about healthcare. And then you also get all the responses inside the topic. So here's what people were actually writing, but we don't want this because it's too much to read at scale, so we can do better. Topic 6, people said something about service, good, improve, don't, great, need, way. Again, we have an idea, but we actually don't know what they're saying specifically. And topic 8 is something about staff, waiting time, reducing long, probably about waiting time, but we got to figure it out exactly. So, we need a baseline in any kind of data science task. So we had a human go through and just eyeball it and say, what do you think each topic's about? Here's what they came up with. So this is the baseline labels. So they thought topic 4 was about medical services, topic 6 was examples of good service, topic 8 was waiting time. And then we ran our summarizer on every topic, so it produced these automatic free text summaries of what it thinks every topic means. So specifically, in the ones we said, humans said it's medical services. The automatic one said, we need more doctors, nurses, and hospital facilities in all caps. How to improve provincial doctors, need to get pay doctors more and provide more hours in the clinics. So the really big difference between the eyeballing and the automatic summarization is that we have concrete details. So concretely, the summarizer told us people want to pay doctors more, they want more doctors, and they want more working hours. And just by looking at the word cloud and looking at the eyeballed label, we would not have got that insight. The good service one is basically saying, service is good, I don't know, it doesn't need any improvement, so that's fine. And waiting time one, it says, staff take lunch breaks at bad times, phone wait times are too long. So we already knew somehow that was about waiting times, but by looking at the summarizer, we can see that the top problem is that the phone times are too long and that they need to move the lunch break because maybe people go to the office at lunchtime. And this one's a very important one, which is how we do statistical analysis, where we say for every topic, what was that? Remember, the second question was rate the service out of 5. And this is how the service rating is correlated with which topic they talked about. So you can see if a slope is this way, going down, it means most people ranked at top with a score of 1. And if the score is going this way up, it means most people were happy about the service because most people ranked at 5. So if we look at this, medical services, people are basically very unhappy. Topic 1 and 2 make up a huge majority of how people feel about medical services. Good service, people mostly feel happy. And on waiting time, people feel average. Actually, one of the most common ones is 3 out of 5. So you can see it really puts a big difference on the sentiment of how people felt. So that's it. That's actually the whole case study. And so if we recap, what we've learned now from this huge automatic noisy corpus is we automatically figured out what did people want to talk about, what topics using LDA, how many people talked about it just by counting the proportion of population, how do they feel about it against normal statistical analysis, and finally, actual automatic summary of the main details using summarization. And so that's basically this pipeline, filtering data, encoding the data, doing the topic modeling, scoring it, throwing out more data, and then finally we do the summarization and analysis down here. So actually most of this pipeline up here is just trying to figure out what data is important and what can we throw away. And so we finally, by using this, we can throw away this huge survey and just give our customers a very small amount. And actually, there's a very interesting influences from this, because actually, not only do we have the obvious benefits like automatic analysis, cheaper analysis, we also have this impact where if you don't put any effort into writing a response, your response is going to get thrown away. So the only responses that get kept are people who care a lot and put the time in to write a proper response and a long document. And because of this, the positive impact is it's kind of less democratic, but the more vocal voices are heard, so you get better data. But the negative side is that very small groups will get left behind. And this is actually a very big point of controversy amongst machine learning communities, that sometimes the algorithms work very poorly for small communities. So you might have a blind community, which is just a few people, but they have a very large problem, but the summarizer will not pick it up, and because humans aren't looking at it anymore, it just gets completely missed. So that's a big warning on these kind of techniques and methods, but I don't know how to solve that. So it's a good thing to think about. And that's it. Any questions?
Thank you for your talk. We still have books. Maybe last one.
Thank you for a great talk. Well, how do these techniques and algorithms work with languages that are much harder to split into words like Chinese, that doesn't have spaces between hieroglyphs, and you don't know if it's ending of another word or beginning of the other?
Right, thanks. So actually, yeah. So I actually did my undergraduate thesis in Arabic, natural language processing. And what you'll find is that if you look at the pipeline we have, the only thing that changes is how we clean the data and encode the data. Actually, everything underneath, at this point, everything is just a matrix of numbers. And that is the same for every language. So just how do you get the sentence into the matrix numbers? And basically, every language has its own body of research. So for Chinese, for example, there's actually specific things that break up words, sentences into words, even without spaces, using heuristics, rules, and machine learning. And so basically, you just change the first part for your language, and then everything else is the same.
Hello, thank you for presentation. I have a question about accuracy. Can you give information about that?
Yeah, so this is very difficult accuracy because this is unsupervised and there's no ground truth and no labels. Because, it's like, here's a survey, give me a report on what people said. There's kind of no real truth in even the physical sense. And I guess in research papers, the way they do it is they kind of compare. Actually, there's one thing we did. Because this survey had a classical analysis using analysts, and then we compared our analysis. And what we did find in this specific case was that we captured not only everything the analysts found, but we also captured additional topics that they missed. So in this case, it was pretty good, but in general, it's hard to numerically measure it more than a sentiment.
Hi. Thanks for the talk. And my question is, what was the actual technique for sentiment analysis in statistical analysis of satisfaction part of?
Right. So we did actually try like a normal sentiment analyzers, like the Stanford Sentiment Analyzer, which just uses dictionaries. But actually, in our case, what we did is in our survey, we actually just asked them to rate 1 to 5. And we found that just doing this, it kind of removes a lot of noise and gives you a lot stronger number. So that's what we did.
Thank you for your question, guys. We're out of time.